Alright, so we've seen how to share a classical secret using a quantum state. Now let's see how we could share a quantum secret using quantum states. So it's going to be a little bit challenging, and in particular we're going to need to use 3 different parties among which to share the secret. And I'll tell you a little bit later why we needed 3, we couldn't do it for 2, and you can think about it already. So let's take a secret that's a quantum state, and for this scheme we'll assume that the quantum state is a trit. There's 3 possible basis states for our space of secrets: 0, 1, and 2. And our goal is to distribute this secret into a tripartite entangled state that's shared between Alice, Bob, and Charlie, such that each of them has no information about the secret, so the reduced density matrix should be independent of the state that's originally shared. But any quantum state I should be able to recover from the tripartite state if I have access to all 3 shares at once. So here's a scheme that will let you do this. I'll explain what the encoding is on basis states first. So let's take secret which is equal to 0, and we're going to share this secret using the state 1 by root 3 normalization, and then a superposition of Alice having a 0, Bob having a 0, Charlie having a 0, or Alice, Bob, and Charlie each having a 1, or Alice, Bob, and Charlie each having a 2. Okay, so that's the encoding of the 0 basis state. Now, let me tell you how to encode the 1 basis state. I'll use the little bit shorthand notation here, so we're going to encode it into the superposition of 0, 1, 2, shared between Alice, Bob, and Charlie, plus 1, 2, 0, plus 2, 0, 1. And a 2 I'm going to encode as 0, 2, 1, plus 1, 0, 2, plus 2, 1, 0. So these are my 3 states. So the first thing to verify is that these 3 states are orthogonal, so they let us recover the original secret S, when S is the basis states. So now if the secret is not a basis state, if it's a superposition alpha 0 times 0 plus alpha 1 times 1 plus alpha 2 times 2, then I'll simply encode it into the same superposition of the 3 states here: alpha 0 times the first state, alpha 1 times the second state, alpha 2 times the third state. And you can check that in this way there is a perfect correspondence between any pure quantum state in C3 and certain states that are shared between Alice, Bob, and Charlie. So we can do perfect recovery. The other thing to verify is that the secret sharing scheme is secure, meaning that the reduced densities on Alice, Bob, and Charlie are independent of the secret. And that's easy to check, because for each of the 3 states that I've been using here, the reduced density on either party is simply the totally mixed state. So it is always the case that Rho A is equal to Rho B is equal to Rho C is 1/3 of the identity. So this is a valid secret sharing scheme, and it encodes 1 qubit into 3 qubits. Now actually, this scheme has a property that's stronger than what I've been telling you so far. What we've seen is that you can recover the secret by taking all 3 shares together. Actually, you can recover the secret from 2 shares only. Let's see how we would do this. For instance, let's just suppose that Alice and Bob get together and they want to recover S. Here's how they can do it. So if Alice and Bob are together, they have these 2 qubits here. And note that in the first case, if I compute Bob's trit minus Alice's trit, I recover the secret. So a way to go from here to here is to simply compute the difference B minus A. And now this works in all 3 cases. If I look at it here, I compute B minus A, here I will get 1, here I will get 1, here I get minus 2. I do the computation modulo 3, minus 2 is the same as 1, and so I recover 1. Here again, take the difference, and it's always equal to 2. Here I get 2, here I get minus 1, which is the same as 2, and here I get again minus 1, which is the same as 2. And you can check that because my encoding is permutation invariant, this decoding procedure, simply taking the difference of the 2 shares, is going to work in all 3 cases. So actually I can always recover the secret from 2 of the qubits. And that's not a coincidence. Actually what I've described to you here is more than a secret sharing scheme. It's an error correcting code. And it's an error correcting code that's secure, or that's correct, with respect to deletion of 1 of the 3 shares. And this is exactly what's happening here. We can recover the original secret even if we lose one of the shares. Okay, so that's quite interesting. We've managed to encode one secret into 3 shares such that the secret can be recovered from any 2 out of the 3 shares. Now I'll let you think about generalizations of this. The theorem that you can prove is that for any number of parties n and the number of shares k, such that n is strictly less than 2k, you can distribute S in n shares in a way that you can perform recovery from any k. And we saw the simplest example of this theorem, which is, in our case, we had n equals 3, k equals 2, and you can check that indeed it's the case that 3 is less than twice 2. Now why this restriction? See that the theorem doesn't let us share anything between 2 parties, because if n is 2, k has to be at least 1, there's no way this inequality is going to be satisfied. And the reason for this impossibility is related to the no-cloning theorem. If you could distribute a secret in between 2 parties, such that any of them by itself can recover the secret, then you could recover 2 copies of the secret. So you would have created a cloning machine. And that's impossible. So no-cloning theorem is the condition that explains why this is a necessary condition. Now the fact that it's a sufficient condition, that's the theorem, and I'll let you think about it. If you're able to generalize this scheme, it's not completely trivial, but using ideas from error correcting codes, you can do it.